Welcome to Ask and Learn.
Okay, so with this problem, you have a slab and with some thickness to it that's not conducting, so the charge is just like kind of uniformly hanging out in there. And your goal is to get the electric field at different points from the center of the slab. So in each case, you basically want to use Gauss's law, and your Gaussian surface is going to be a rectangular prism. So this is at some representative radius r. It's going to look like that. So that would allow you to find the electric field all along here at some distance r. I'll just do that in a different color. Okay, so here's some distance r. So we want to use Gauss's law. And so that says that the flux through a surface, the integral of E dot dA, is equal to the charge enclosed over epsilon naught. And actually, before I forget, I'm going to try to get better at doing this. I want to write down all the relevant constants so I don't have to refer to the problem. So this total thickness, D, is 9.4. These problems just get so exciting. You just want to dive right in, right? Millimeters, and that's 4O. And you're given rho, the charge density, is 5.8 femtocoulombs, so times 10 to the minus 15 per meter squared. And I think those are indeed the only givens. And then you want to find it at 0 to 4.7 and then 26. So I'll write that down. R equals 0. That was supposed to be a question mark. There's some like timing delay when using this tablet that makes it hard to precisely write. So R equals 0, at least quickly. And then I, for the life of me, cannot remember these numbers. 0 to 4.7 and then 26. Some numbers just really don't go together. And these all have 3 sig figs. I forgot the sig figs here, but not super important, so I'm not going to redo it. And then these are all in millimeters, 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 millimeters. Great. And I'll just go ahead and put that in a little box. Okay, so when we're considering the flux, we want to think about the field's shape. By symmetry, the field has to be outward. And I guess I'll go ahead and draw that. So it's like we don't know its magnitude yet, but we know it's by symmetry. It has to be outward. It can't be like up into the right because of the symmetry of the problem. There's probably a lot more on that in the textbook, but anyway, I'll just leave that there. So we know that that's basically going to be the direction of the field. And so we know that only this and this are going to get, this front and back face are going to get flux. And so we want to kind of come up with a formula for how much flux. So consider the Gaussian surface with the area A. Each of these is going to get the flux, so then the total flux is just going to be 2EA, and then E is constant by symmetry, translational symmetry, all throughout here. So you have 2EA equals Q enclosed over epsilon naught. Charge is equal to the volume density times the volume, and so that's area times R. So the more bigger your R, the more R charge you're going to enclose until you reach D. Epsilon naught. Great. And so now you can have a formula for E. E is, not sigma. I've written sigma so many times for the other problems. Oh, why is there a delay now for erasing these? Okay, so sigma. Oh, and then the A's cancel, which is good because, we're not really given an A. So I'll go ahead and write that out. Sigma times R. Oh, sorry for that ugly R. Oh, and then it's actually would be 2R. The size of the box is 2R. So there's another 2 here. So these 2's also cancel. So then you're just left with an even simpler formula. Just rho R over epsilon naught. Great. And so then basically for A, R is 0, so E is 0. For B, R is 2 millimeters, so 0.002 meters. So you plug that in for R, plug this in for rho, then your epsilon naught. And then I get that E is equal to 1.31 times 10 to the minus 6 coulombs per meters. No, not meters squared. It's kind of hard to coordinate all of the performance of physics and also doing it. Newtons per coulomb. There we go. Okay, and then C, again, we're like still in the slab with C at 4.7 meters. Oh, are we actually still in the slab? I originally thought that, but so this D is 9.4, and so that means that half of D is let's see, 4.7. So we are actually just at the border. So we're like we're right at the point where we've enclosed all of the charge. And so if you've enclosed all of the charge, then oh, okay, great. So my answer actually doesn't change. I just had the mental realization that you're just on the border of being into and out of the slab. So your R is 4.7, 0.047 meters. And then I got that E was equal to 3.08 times 10 to the minus 6 newtons per coulomb. And then for D, you're totally outside again, but you're not really enclosing any more charge. And so this R goes to D, and then the answer stays the same. So that's the same as C. Just gonna double check one thing. Yeah, so that's how it goes.